Cool. I think we can get started here. So yeah, thank you guys for joining today. So we have Michael here from Baking Bad. Baking Bad is a team that's been around since 2017. They have multiple products. For example, they have Baking Bad, which is like an audit and rating product for Tezos stakers or bakers, and they have like a Tezos Explorer, some SDKs, and some dev tools that they've built out. So Michael today will give us an overview of what they've built. So I think he'll start out with some Tezos specific things to help you learn about the Tezos ecosystem. Then he'll segue into some of his products and do some live coding with Jupyter. So yeah, thanks and take it away, Michael.
Thank you very much. Thanks for having me, and thank you very much for joining. As Spencer said, I'm from the Baking Bad team, and we are one of the contributors to the Tezos ecosystem. And we, among other things, we are working on several developers tools. So you've probably heard about our Explorer that are called Dev, which is designed specifically for contract developers. We also have several SDKs for Python and .NET. And recently we released a Michelson support for the Jupyter notebooks. And lastly, we have handy faucet bot for testnet development. So I'll now switch on my presentation. So you're not going to see me anymore. Okay. So yes. Just a second. All right. So this is the list of the developer tools that we maintain. So you can find more info on our site. And today I'm going to present you a few things. First of all, we are going to discuss several important concepts of the Tezos virtual machine, things that we believe developers should know before they start writing contracts on Tezos. And then we will move on to some practical stuff. We will write a simple contract in Jupyter, and then we will do some things with it. So we are going to deploy using the Python SDK and then interact with the contract using just your browser. So let's begin. Michelson. So what's so special about the Michelson? This is the native language for the Tezos virtual machine. It's very different from other cryptocurrencies. So it's, for instance, very different from the Ethereum virtual machine bytecode or WebAssembly, and it's actually a high-level assembly. But Michelson offers a rich set of safe types, such as inbound integers, lists, sets, maps, and more. And in fact, many of these primitives are tightly bound to the according primitives in high-level languages such as Lego or SmartPy or anything else. That's why I believe since it's highly likely that you're going to write contracts using high-level languages during the hackathon, it's still important to know what's happening under the hood, because these internals can keep you safe from some possible mistakes or some probably design misconceptions. Right, so we are speaking about their Michelson rich type system. And in addition to that, Michelson has a very strict type checker that runs before every contract execution or contract deployment. Combined with the rich type system, it allows to catch many bugs in the early stages before you even deploy the contract to the network. And finally, the thing you should know that Michelson is purely functional, meaning that the contract has no side effects. So this is both an advantage and a limitation because, for instance, it prevents such things like reentrance attacks. And on the other hand, it disables asynchronous calls, for instance. Another thing, that contracts do not return value in general sense. So a contract receives its current storage, like a state, and some input value, it's called parameter, and returns a new version of the storage, plus a list of spawned operations. They are also called internal operations, which are basically subsequent contract calls. Okay, so this is like basic things you should know about Michelson, and then we are moving on to another important thing, and this is gas and storage limits. I want to pay an attention to this thing because this is very different from other blockchains in a way. What are gas and storage limits? This is basically you saying that your contract won't consume more resources than specified in your operation. In addition to that, there are also maximum limits per single operation and per block. They're called hard limits. What should be noted that both the type checker and the Michelson interpreter consume gas. And in addition to that, you have to pay for every byte written to the blockchain, whether it's the contract storage or a new account. It's also called contract allocation. In fact, this is not like you pay this money, but you burn this instead. So it's also you can see the term burning or burn cap, something like that. This is all about the storage limits and storage difference. Gas and storage hard limits prevent creating a contract of arbitrary complexity, and they also stimulate all kinds of possible optimizations. For instance, splitting your contract logic across multiple contracts, and other things. As I mentioned, gas and storage limits for a particular operation are specified by the contract caller, and currently the only way to calculate this limit precisely is to perform a dry run. So this is actually you make an operation without applying it to the blockchain. Alternatively, you can, like the other way, you can set limits to the maximum possible values, right? So to the hard limits. But that will cause fee increase, of course. But anyways, it's a good enough approach if you're working in testnet, because test coins cost nothing. And especially if you're just working on a concept and you want to do things as fast as possible. So next, I want to say a few words about the intercontract interaction, since usually there are many questions and many troubles. As was mentioned before, Tezos doesn't allow synchronous contract calls, even read-only. So like view methods in Ethereum. That's why the only workaround right now is to implement the callback based scheme. So in practice, this means that all contract methods that not only change contract state, but also respond to some request must pass the return value as a parameter to the callback operation, right? To the subsequent contract call. And in this case, sorry. In this case, the destination address for this operation is attached to the original request. So if we stay on this simplified scheme, the requester, like the contract that initiates the call, passes the parameter for some contract method, and also he passes like an address, a callback address that is going to receive the value, like the response value. And this is, it's not necessary that this is going to be the same contract at the initiator, but in any case, the developer needs to consider maintaining the request context somehow, right? To in order to know like who has made these requests and etc. etc. And also he needs to consider to protect against possible attacks in the scope. And the other concept that often confuses is entry points. The entry points in Tezos are actually quite lightweight concept, and they are in fact optional. Under the hood, each contract has a single entry point, some sort of main function that receives a single argument of a declared type. So a developer can use so-called union or variant type in order to control the execution flow depending on the value of this input value. And entry points is basically a standardization of using this type at the protocol level. So that's why you can call a contract in several ways with the same outcome, which is both confusing and flexible. And also returning to the inter-contract communication, it's worth noting that you can send to the responder not only the callback address, but you can also specify the entry point that should be called. So the pair address plus entry point is specifying the target entry point for the callback response. All right, and the last thing from the theory is when you're switching to implementing some front end for your contract, you're likely to encounter several difficulties in implementing the front end. And first of all, what's important that there's no built-in mechanism in Tezos to track contract execution. You know, like concepts similar to events in Ethereum or something similar. So you would need an indexer solution to monitor transactions. Secondly, if you'd like to get some data from the contract storage without the direct access, right, you need to implement callback entry points, right? So some kind of view methods on steroids. And this includes implementing a stub contract that will receive the data, and finally you will need to perform a dry run call, which is zero cost, and to parse the parameters of this call. This is a bit confusing and seems like overhead, but right now this is the only method to work around this issue. the other way, you can access the contract storage directly. And in fact, most of the data can be obtained using just the Tezos node API. However, if you use a special data type called bitmap, which is basically a lazy hash table used to optimize large data access, you will also need an indexer to enumerate its keys, as there is no way to do it using just the Tezos node API. Okay, and so before we move on to the practical part, I'd like to give you more sense of how Tezos contracts work. And a perfectly good way to explore the contracts in the wild is our Better Call Dev BCD Explorer, which stands yeah, right. So BCD stands for Better Call Dev. I'll show you some selected contracts to demonstrate everything that we have discussed. And at the same time, I will tell you a few things about key features of our Explorer. Okay. So let's go to the Better Call Dev. Okay. So it starts from the search string. It looks in a way similar to Google. So unlike most blockchain explorers, BCD enables full text search by contract code and storage, operation parameters and operation results, errors, and many other factors that we can see on this page. This is actually high-level entities that you can search in. So you can search for contracts, for operations, for big maps, using these factors and also using these filters. So let's find some contract. So I'm going to search for a contract that has word game anywhere, and I'm interested in mainnet only. All right. Yeah, and I'm looking for contracts. Good. Yes. Okay, that's what I was looking for. So here's some smart contract. So we can tell that it's probably written in smart Pi high-level language, and it's pretty old. There is no activity since January, and there is a similar contract on the mainnet as well, but we are not interested in that. So let's take a look at the code. So how Michelson is actually looks like. Okay, so here's like some pretty formatting component, and we can spot that there are three main sections in the Michelson source code. So it starts with the parameter, which is basically type definition for the contract input value. And then there is storage sections, which is also type definition for the contract state. And after that is going the code, which is the sequence of Michelson instructions. Aside from the blockchain specific things, Michelson is actually a pretty simple stack-based language. I will show you more details of how it's working under the hood a bit later. So let's take a look at the storage. This is an adapted view. So originally it looks like that. This is like a special notation called Michelson. And we can see that there is some data, so some address and strings, Boolean values, and also a data type called bitmap. Okay, so what this contract do? What does this contract do? In fact, this is some implementation of the tic-tac-toe game. We can see that this is some kind of initialization. So a new game has been created with a blank deck, 3 columns and 3 rows. The players are specified, and after that, the first player takes the move and places some dot on the deck, etc., etc., etc. So the cool thing about the method called Def Explorer that it tries to show you the actual change of the contract state during the execution. So recall that Michelson is the Michelson contract is a pure functional. So here is the input parameter, and this is like old storage, like previous storage, and new storage combined with in a unified difference. You can see the overall picture on this screen. Okay, and I've been talking about big maps, which are lazy hash table structures used for large data storing optimization. So here is a big map viewer where we can explore big map keys and values, right? And we can also check out the history of changing a particular key in this big map, right? For instance, we see that this is the initial value of the deck. This is the state after the first move. Okay, so let's move on to the next contract. And the next thing I want to show you is the example of an interaction between several contracts. Oh, this is not the right contract. All right. So here is the atomics contract, which is actually an implementation of atomic swap protocol for Tezos tokens. And in this particular example, we're working with TZBTC token. So what can we see in this particular operation? We can see that someone has called the initiate entry point of the atomics contract, which has in his turn spawned an internal call transfer of the TZBTC contract, right? So the atomics pass few parameters, right? So atomics said like TZBTC, please transfer this amount of tokens from this account to that account. And we can see that there are some changes in the ledger map of the TZBTC token contract. This is like an example of the communication of two contracts in a single operation. So you can ask, and what will happen if, for instance, this transfer fail, for instance. let's find some operation. Typical example is when there is a gas exhaustion error, when contract spends more gas than the limit inside the operation. Okay, and we're looking for an internal operation. Okay, that's it. So here's also some swap contract. So I don't know exactly what's under the hood, but we can see that there is a chain of 2 internal transactions in this contract call, and since the last one has failed, all the previous transaction have been backtracked, right? So they are not applied. No funds has been spent. All right. So, and the last thing before we will move to the practical part is view methods. So let's check. Okay, so let's find some get balance applied. Okay. All right. So you can remember the example from my presentation. So like that, when one contract calls another contract and then receive the value from the responder. And here's an example, right? So someone has called some contract and he asked to return a balance for a particular account, and also asked to return value to this contract. And we can see that this destination contract has made an internal call with the parameter holding the value of the balance for this particular account. So there is like very common example of using view methods in Tezos. All right, so now we will move on to practical part, and we'll start with writing a simple contract. As I said before, it's likely that you will use a high-level language to write a contract during the hackathon, but I believe that knowing what's happening on low level will help you to understand some design choices of these high-level languages, and well, like in general, it will bring more sense to you. So we are now in Jupyter Notebook. This is an awesome environment for some experiments and prototypes. And recently we have released Michelson support for this tool. Okay, so what I want to write is a contract that can receive and store some data, and also that implements a callback method for retrieving data from the contract storage. Okay, so recall how Michelson contracts look like, right? So we should have like 3 sections. first the parameter storage definitions and then the code sequence. So let's do that. So first of all, we need a contract type. And as I said, I will need two methods. The first one will be called set, right? And this method will receive a key of type string and a value also of type string. And the second entry point will be called get. And we will pass also a particular key. And in addition to that, a contract address, a callback address that will receive the value, an according value for this particular key. Okay, so we have our parameter type. Then storage. We will have like a simple map of string, and we will use this special type big map for storing large data in order to demonstrate what's so special about big maps. So as I said, a contract in Tezos receives a pair of its state or storage and the input value, the parameter, right? So in Michelson kernel, we can do some sort of simulation of this execution workflow, and there is a special helper called begin, and we will firstly debug this set entry point. World. Okay, and so there is going like empty storage. The initial storage is going to be empty. Okay, so here's our stack, right? We also can print the stack. So as was mentioned, Michelson is actually a stack-based language, so you can work with the stack machine as in any other stack-based language. It's pretty straightforward. The only difference is that you have to keep in mind all the types and elements on the stack. And in that sense, the Jupyter is a perfect tool for managing this kind of things. All right. So I'm not going to spend much time on the syntax and semantics. My goal is to show you the general contract structure and what has actually happens during the contract execution. So now I'm going to write some code. Just a sec. All right, we have done some stack operations, and now we have more values than we had before. So we have unpacked the initial pair of parameter and the storage, and now we are going to handle different different execution workflows. This is actually the thing I was talking about entry points, right? So, like basically, contract has a single entry point or main function, and in order to implement some different execution flows, you can use like a special union type, and then you have to dispatch this this parameter using special instructions. And in fact, this OR primitive is this union type. And what we're going to do is to check if this set entry point invocation or the get entry point invocation. And this is actually the way when we're dispatching this data. So now more scary instructions. Okay, so what we have done actually is that we have processed the input value and put the value for the corresponding key to our contract storage. And now all that we have to do is to build the resulting value for the Michelson contract. This is the pair of the new storage and the list of internal operations. And after that, we can finish the execution. And please note that the result of the contract execution is not only the new storage and list of operation, but also the thing called big map difference. This is actually, since big maps are lazy data structures, in the execution result, you see only the keys that have been altered during the execution and not the entire storage. Okay, and the second branch is going to be a bit more complicated than that. So we need to hurry. So in case of the get entry point, we need to get the value for the corresponding key, of course, if it exists, and then we have to create an internal operation that will send this value to the receiving contract. All right, so, okay. Don't worry, you won't you won't do that because you're probably going to use some high-level stuff, but nevertheless, this never hurts. Okay, and so this is actually the instruction that will spawn a transaction operation. All right. So let me switch to the get entry point. So I want to get a value for the key bacon, and I want to receive the result for, so it's actually doesn't matter what the address is going to be like. I just need like a valid Tezos address. Okay, and I will make an initial storage with that key. Okay, so continue the execution and okay. All right. So in the end, you can see that we have this internal call with parameters holding the bad string. So we have our contract, and now first thing we want to do is to deploy to the network, and then to do some interactions. Okay, so now we're going to use Google Colab, which is basically Jupyter environment in the cloud. It's very handy. And if you will use Tezos library and any other tooling from us, I highly recommend to use either Google Colab or Jupyter on your local machine. So first of all, we need to install some crypto libraries. This won't take long. After that, I need to install Tezos and to import a few things. While libraries are installed, I'll start to write some code. And the first thing you should know about Tezos that although there are some docs and articles we have published, we've tried to design and make Tezos in a way that you don't actually need to read documentation, because the docs are actually built in to the library. So anytime you have doubts about some methods or class, you can just type the variable, and you will see all the properties and the helpers that are available for this particular class, instance, or function. So what comes right out of the box is some built-in Tezos node RPC endpoints and a predefined key with some coins on the balance that can be used to interact with contracts in Tezos test networks, like CartridgeNet or ZeroNet or any other future networks. Okay, so first thing we should do is we should import the contract that we have written in the Michelson kernel. So for that purpose, we have this contract, that class contract, that can be can be constructed from several sources. So I have chosen to initialize the contract from the Michelson code. Yeah. Oh, you can also initialize the contract from a file or from the Michelson JSON notation. So I need to move the code from storage, and finally the code, which is okay. So next, the main and finally the player. Okay. Yes. So we are good to go. So here's the Tezos contract class, and we have an instance of this class that have several properties and methods. And let's take a look. So we are now interested in deploying the contracts, and for doing that, we will need the contract code itself and the initial storage value. So I have a slide for that. Okay, so in Tezos, there are several types of operations, and one of them is called Origination, which is used for contract deployment right now. It requires, among other parameters like gas limit, storage limit, and fee, it requires script which consists of the contract code, right? Which in his turn contain 3 sections: the parameter and storage type definitions, and the code, which is the sequence of Michelson instructions. And we also will need the initial storage, also in JSON format. So in Tezos, these kind of things are wrapped in some sort of abstractions, so you won't need to deal with Michelson values or JSON strings, and you will be working just with the Python types. So for instance, let's take a look at the contract storage object. We can see that there is a section which is called Python's docstring, and it tells us which Python object, which is the corresponding Python object for this particular storage type. And there also has a useful method default that can generate a default storage for a contract, which is very useful when you have to deploy contract at first time. And we can see that the default storage for this particular contract is just like an empty list, which is logical, right? So, okay. What we are going to do is to make an origination operation. And here is the methods. Okay. So the the autocomplete is not working. This is okay. So we can do this. This is like a small docs for this particular methods, and it says that it accepts several parameters, and as I mentioned, it requires a valid script and like initial balance and the source and other parameters. So what we're going to do is to pass just the script. Okay. Right, so we now have partially filled payload for the origination operation, right? So we can see that few fields are not filled yet. And of course, we don't want to fill them manually. And for this reason, there is a helper called autofill. Right, it's listed in this list. So we can first see what does this method do. It said that it fills the gaps and simulates the operation in order to calculate precise gas, storage limits, and fees. This is the thing that I told you in the very beginning. So let's do that, and we can see that now fields are filled with the values. So there is some gas limit and a fee and other useful fields. So now what we need to do is to sign the operation with the built-in key. Okay, so we have the signature. So, and the last thing is we're going to inject the operation, which is like the synonym for broadcasting transaction to the network. And yeah, and so we have a hash of our operation. Let's go to the BCD Explorer, and it usually takes some time for the operation to be included to a block. So typically several seconds. So we will wait for a while, won't take long. So while the operation is pending, there's also a way to do this with waiting for actual injection. So there is a parameter is sync, which is true by default. You can set this parameter to false, and then this inject method will wait for the operation to be included to the blockchain. Okay, so I guess we are good to go. Oh, still not. Okay, we'll wait. So it actually, we're not now working with the cartridge testnet testing network, and sometimes there are large gaps between the blocks. Okay, so our contract is on chain. Oh. Great. Okay, so here is the origination operation. We can see that we have like empty big map, and we have burn like some amount of tests because we have actually written some data to the blockchain. This is our contract code. So let's take a look at the contract. So here's the code. It's exactly the code that we had written. Here are the entry points. So here's the get and the set. All right. So now we are going to make some contract calls. And first of all, we need to make some sort of contract interface. To interact with the contract, okay? So this is actually an automatically generated contract interface for our particular contract. And you can see that we have 2 entry points then that we can call. So let's start with setting some value. So we can look what's the actual parameter for this call. And it says that we have to pass a key. So like that, and value like that. All right. So here's the payload for the transaction operation. And in this case, this is going to be a bit similar. We just type inject. And yeah, we're good to go. It's going to take some time as well. And hopefully we'll see that our storage will change. Okay, so this is also a cool feature of the BCD Explorer. It shows you the operation while it's not on chain, but in some Tezos node memory pool. So, and that's why we can be sure that our operation is not lost, that it's still pending, and we can wait. So here's our parameters, and we can see the limits, the gas limit, the storage limit. So it seems that we are going to write this amount of bytes to the context. And since the operation is not applied, we have not burned coins. So let's check the status. All right, it's applied. Right, and we can see that our big map storage have been changed, and we now have a key with the value with the key hello and the value world. We can also inspect the big map, and yeah, cool. So now we're going to query the so now we will test the get method, and for this purpose we need to use some third contract that will receive this particular value. Just a second. I will not do like second deployment because I already have a contract. Okay, so I will find this contract, the BCT. So the other cool thing that you can search contracts using just type in first letters of the contract. Oh, okay, so here is our contract. All right. So what we're going to do is to see what's the method signature of the get entry point. Okay, so we need to pass the key and also the callback address. Okay. So we have a payload, and in that case, we actually don't need to have a actual operation injected to the blockchain. We just need to simulate the code, and for that purpose, there is a useful helper called view, which we can execute and receive the target value. So this is the last thing I'm going to show you is the direct access to the contract storage, and you can do that with just using these helpers. So what's that? You can ask. This can be confusing at first. This is actually the pointer to the big map storage of our contract. Since it's a lazy structure, it's not returned in full by default, but it returns the pointer to the structure instead. So if we want to get some data from the big map, we will need to use this method. Right, so note that I know the key, hello, but in case I didn't know the big map keys, I would need an indexer to enumerate all the keys, and only after that I will be able to query the data. All right, I think that that's going to be all because we're probably out of time.
We have like 8 minutes left before the webinar will cut off, I think. So it seems like there are some questions from some people here. If you want to answer them, and yeah, we can answer for 5 minutes, and then we can wrap up. All this stuff will be recorded and put on YouTube as soon as I can, and so you guys can review the material if any of it was confusing or anything like that. So yeah, so if you want to answer some of the questions.
Thank you everyone who stayed so long till the end. Really appreciate that, because in fact the material is quite tough, I believe.
Yeah.
So there are a few questions from Rafael. There's an example of tokens launched traded on a.k.a. 1.2, and if it's needed interconnectivity for its contracts from other blockchains for such. All right, so I've shown you the Atomics contract, and this is actually a way to bond together tokens from the different networks through the Atomic Swap protocol. So the Atomics implementation is open source. It's on GitHub, so you can take a look on how it's implemented. There's actually implementation for the Tezos, FA 1.2, and USDC token on the Ethereum blockchain. Concerning managing contracts, I'm wondering about depth architecture, which would storage in a DB contract addresses published. I'm not sure I got it correctly. So if you could ask differently. So concerning the Tezos, how would you suggest to set up a configuration for it in a large scale project at the context variable? I've been reinitializing this config every time. Although there is like some sort of predefined configuration in the Tezos with a key and the network endpoints, it's actually very flexible. So and also it's how would I say it? Well, it's easy to embed in a larger project. So there is some docs on the in the GitHub. You can also look at through the code because it's actually very straightforward, and like you're also always welcome in our chat when I will answer your questions as quickly as I could. Okay, so yeah, so let me turn the screen sharing one more time, and I will show how to configure the Tezos for a particular shell or the key. So there is a special method called using. Oh, just a second. And it actually returns a new instance of the Tezos client, and you can specify network. This is one of the predefined values, so you can use like mainnet, zeronet, CartesNet, or you can actually construct. You can also use sandbox net, which stands for the default local node. Moreover, you can use like this notation, so you can write like localhost, and it's going to work too. As for the key, you can write like the encoded private key in the form of ED and then some base 58 encoded value, or you can pass some path to the, for instance, faucet JSON file, or I don't know. You use, for instance, if you have like a Tezos client on your machine and there is a key with an alias, you can use Tezos client alias for the key. So there are multiple options, and like the usual workflow is to do like that. Okay, so you kind of redefine the default client, and then you work with this client. But you can also like create custom clients, and all these clients will be isolated, so you can use either of them without worries that something is going to be overwritten also. So something like that. Hope I've answered your question.
Awesome, cool. We have 1 minute left. Thank you again for your time, Michael, today. This is super helpful. And for everyone else who's attended, thank you for coming. And we will have 8 more workshops from here. It's going to be Monday, Wednesday, Fridays, and the last one will be on a Tuesday. It'll be all at the same time. You can find all the workshop schedules on the Google Calendar. And yeah, the hackathon itself will start on May 25th and run for a month until June 25th. There will be a number of different programming during the event as well. And we will likely have a team building session next week for those of you who are looking for teammates. But yeah, thank you again for your time. And yeah, we'll catch
Thank you very much for having. Yes, I wish everyone good luck and have a good month of hacking. And yeah, feel free to ask any question in the CoinLab Discord channel or in our Telegram chat. So everyone is welcome.
Awesome.
So, cheers.
Cool. Thank you guys. Have a good one.
Goodbye.